Welcome back, fellow gardeners, computer touchers, colleagues, and fellow homunculi. I'm being tested today, I'm not gonna lie. This is like the fourth take. Software crashes, nonsense. I never even get past the first problem. Tons of lag, Hackintosh problems. But I refuse to use an inferior operating system, so we're just gonna deal with it. This is 36 random LeetCode problems, ones I've done before, of course. Speedrun any percent. Okay, some of these are going to be optimal space and time complexity, but this is any percent, so some of them are just going to be YOLOs. It's just gonna, if it gets the problem done, then it's good enough, right? So I have them all loaded up on top here. As we finish them, we're just gonna close a tab. There's no code up or anything like that. I get no benefit from cheating or any nonsense like that. This is purely a intellectual flex. Okay? No, I'm joking. This is just practice. So I'm going to start, and we'll see how far I get, honestly. I'm not even sure. Let me see. Oh, wait, my thing isn't even updating, bro. My timer only updates when it's on screen, bro? Oh, that's so cheeks. That's so cheeks. Alright, you know what it is, man. At this point, I don't even care. It don't even matter. Given a non-negative integer x, compute and return the square root of x. So I've done this problem before. You can phrase it as a linear search problem, and then linear search, and then you can turn it into a binary search problem for log n time complexity. We have to make sure that if x is less than or equal to 1, right, that we return x, right, because 0 is squared. The square root of 0 is 0, and the square root of 1 is 1, right? So there's no point in wasting time on that, right? And so to layer the binary search on top, we're just going to do let high is equal to low is equal to 1, high is equal to x, while low is less than high. What we're going to do is we're going to calculate the midpoint, which is going to be low plus math.floor high. We're going to need another one, actually, high minus low over 2. And so this is going to give us preference to the left-hand side, right, when we're doing our splitting. And so if mid to the second power equals x, right, then we're going to return mid. That means we found a good square root on the first try. Else if mid squared, right, is greater than x, means we went too far, so you have to cut off the other half of the binary, cut off the other half of the problem space, right? So we're going to say high is going to be equal to mid, right? Else if mid squared is less than x, right, then the solution here is to make low equal to mid plus 1. We're only adding 1 on this case, right, because our mid calculation favors the left-hand side of the left-hand side of the tree, left-hand side of the problem space, right, when we're choosing because of the math.floor. So we're going to return low minus 1. I did this problem a few days ago, so it shouldn't be too bad and pretty good. I just tried it a little while ago as well. Easy mode, log n time complexity constant space. So I'm just going to close that and go to the next one. Okay, given a binary tree, check whether there's a mirror of itself, symmetric around its center. For example, this binary tree is symmetric. The following. Okay, so I'm pretty sure in this problem we just have to check if root equals null, right? And then empty binary tree symmetry wise is going to be return true, right? Otherwise, we're going to return is mirror and pass in root.left and root.right, right? And then we have to define is mirror up here is going to be a function, right, which takes left subtree and a right subtree, right? And then we have to do some checks, right? So we have to say if left equal null, right, and right equal null, right, then we know that these are we know that this is symmetrical, right, because both left and subtrees are missing, right? However, if left equal null or right equal null, right, then we know that we have to return false, right, because this first case, right, we know that none of them exist. Well, both of them don't. At least both of them aren't missing, right? And so if we get to here, we know that at least one of them is. If we actually execute this case, right, we know that at least one of them is missing, right? So you're going to return false because only one of them exists. Would mean that the symmetry is not there, right? And so to make sure that the symmetry actually is there, right, you have to make sure, right, before we even check if these left and right nodes are symmetrical, we have to make sure that their values are symmetrical, right? Because we can be asymmetrical with structure and asymmetrical with value, right? And so we have to do 2 is mirror calls here. Is mirror, and then here we're going to pass left dot left, right, and right dot right. Why are we doing that, right? Because when you're checking if a tree is symmetrical, you want to check the left node with the left subtree, right, and the right node with the right subtree, and the left node's right subtree with the right node's left subtree, right? So you have to make sure that's happening, right? And then we're going to concatenate basically all of these cases together, right? And if they're all left dot right and right dot left, ooh, this case is kind of long though. And then I think this should work. True. Boom. So this is going to be linear time complexity, right? Where n is the number of nodes that is in the tree, right? It's also going to be linear space as well, right? Where n is the number of nodes in the tree, right? Because we're paying for this with recursion. So each recursive call is going to add a stack frame to the runtime stack, right? So I'm just going to reset this so the next time I do this, I can restart. Given the root of a binary tree returns maximum depth, the binary tree's maximum depth is the number of nodes along the longest path. Let me check my timer still going. Binary trees, maximum depth is the number of nodes along the longest path, the root node down to the farthest leaf node. Okay, this one's not too bad, right? So this one you can just return a function, a recursive function, which is going to do the work for us. You don't have to check anything beforehand, right? Because the function is also going to do that for us here. So we can do count depth is equal to function, right? And we're just going to pass in a node, and then we're going to define a function. And so the idea here is we're going to have each node count the depth of its children, right? And then its children are going to return those values. We're going to add 1 to them, right? Because the children don't know that they have parents. And then each node is going to return the max of that function, right? And so if node is null, we're just going to return 0, right? So if the node is 0, right? If a node is 0, which, like, if you look at any of the leaf nodes, right, their children are null, so we're going to return null, right? So when 9 calculates its depth, it's going to be equal to 0, right? Because it's only going to be equal to 1, right? Because it has no children. And so this is what this case is for. And then here it's pretty simple. We can return the math.max of count depth, right, node.left, right, and count depth node.right. And we have to make sure not to forget to add 1 here, right? Because these children are going to count their depths without knowing that they actually have a parent. And so I think this is pretty good. And so this is also going to be linear runtime, right, where n is the number of children in the tree. Also going to be linear space, right, where n is the number of children in the tree with recursion. So I'm going to reset this one. Next time I do it, I'll restart. I don't do these problems every day, but I try to review them occasionally so I don't forget. So given non-negative integer number rows, generate the first number rows of Pascal's triangle. So Pascal's triangle is unique, right, in the sense that each list, right, starts with a 1, or the left side of the triangle starts with 1s, and the right side is also 1s, right? So if you visualize this as a list of lists, you can just set the first element of the list to 1 and the last element of the list to 1, right? And then other properties to note, right, are that num rows. All right, so if we get asked to generate 5 rows, right, these are 5 rows of Pascal's triangle. Each row has num rows elements, right? So in the 5th row we have 5 elements, and the 4th row we have 4 elements, right? And so what we can do, right, is we can catch some base cases early here, right? So if num rows, right, is equal to 0, right, we're just going to return an empty, what do they want us to return? A list of lists, right? And so if num rows is equal to 0, right, then we're just going to return an empty list. If num rows is equal to 1, right, we're just going to return this value, which is going to be the proper value for Pascal's triangle. And then one more, right, just for 2. And that's going to be that for catching those cases, right? Important to do these, right? You don't have to, but you especially have to do 0 and 1. You don't have to do 2, though. But once we get here, right, we can go to just generating Pascal's triangle, right? And we can say let p sub t, right, is equal to, and we're just going to give it the general values to start, right? And then for here, I haven't done this one in JavaScript before, but here we want to do let row is equal to 3, right? So we're with num rows, right, we're already pretty much taking out 0, 1, and 2, right? So our row is going to start at 3, right? So if we make it past here, we can assume that we have at least 1 row to do, right? And so what's important here, we're going to do row is equal to 3, right? Row is less than num rows plus 1. And since we want row to represent the actual row, but we're actually going to be working with the row minus 1, right, for the actual row. We're going to do row plus plus. And here, right, what we're going to do is we're going to create the row list, right? Add values to list, generate values based on previous sums above, right? And so we have to create row list, right? So we'll call let row list, right, equal to, an empty array. I actually don't know how to make an array of size row in JavaScript, so hopefully that doesn't become a problem. Actually we can do it at the end too, so it actually doesn't even matter, I think. Actually don't know how to do that. Add values to list. So row list, right? We're gonna give it the first value of 1, and so we'll have to add 1 at the end, I guess. Add 1 at the end. This is a JavaScript specific syntax thing that I'm forgetting here, but we'll try it anyway. I don't think I've ever done this one in JavaScript before. So here we have to actually generate the inner workings of Pascal's triangle here, and so what we're gonna do is we're gonna say let I is equal to 1, right? Why are we starting at 1, right? Because we know that the left hand side of the triangle is already filled in. We're gonna have to fill in the right hand side later. I is gonna be less than row, and then we can do I plus plus. Is I gonna be less than row? So we want to iterate in here. So if row 4 is gonna go to 1, 0, 1, 2. Okay, I is less than row. I guess that works. Row is gonna be set to 4, 0, 1, 2. I think we can do row minus 1 here actually. And then for here we're gonna do. Actually, it'll be okay. Actually, I think we can just do row and then change the last index to 1. So we're gonna do row list, right? Dot append, and so to actually calculate the values of the list before, we have to actually summate the values in the previous list, right? And so what's cool, right, is what we can do is we can say p sub t, right? Sub row minus 1, I believe, because we're in the, let's just say we're in the third row, right, which is index 2. So 2, we want to get this value right here, which is going to be 1. So we have to do, actually have to do row minus 2, right? Sub the index right above it. And so we can do I. Yeah, that looks good. And then we can do p sub t sub row minus 2 sub I minus 1. I think we should be good there. And I think we just have to make sure to do row list sub row list dot length minus 1 is equal to 1. And then we can do p sub t dot append. Oh no, it's not even append, it's push in JavaScript. Row list. Boom. I'm gonna change this to push, and then at the end we'll return p sub t. I don't think this is gonna work. I think we might be off by 1 in the way that we're doing this row list thing. I'm not used to doing it this way. Oh, no way. Oh my god. I'm actually a god brain. First time doing this problem, by the way. That not first time. Clearly not first time, but last time I did this problem was like 10 days ago, but irrelevant. We're gonna move on. Boom. Also, the time complexity for that problem is going to be num rows squared, right? Because there's num rows elements, there's num rows rows, and each element has num rows elements, right? And so we're going to do num rows squared. On each iteration, we're storing a value into p sub t, which is Pascal's triangle. And so that's actually going to be num row squared time as well. So say you have an array price for the ith element is the price of a given stock on day I. Design an algorithm to find the maximum profit. Complete as many transactions as you would like. Buy on day 1, sell on day 5. Profit is equal to 5 minus 1 is 4. Some profit. So I think there is a way to do this. So I think you can use a peak and valley approach here. So what they're really asking us to do, right, is to summate, right, summate actual profit of the list, right? Where is profit? Right, so we can do profit is equal to 0, right? And so they want us to summate all the parts where we can make profit, right? So what does that look like? So that's gonna look like for I is equal to 0, I is less than prices dot length minus 1. And we're doing minus 1 because we're going to be looking 1 index ahead as well. And so when do we know we're making profit, right? When we can sell high, we can buy low and sell high, right? And so if that's the case, right, we have to say if prices sub I is less than prices sub I plus 1, right? That means we have a spot where you can make profit, right? And so to actually get that profit, right, we're going to have to do prices sub I plus 1, minus prices sub I to get the actual possible profit. And I think you can just return profit here. Oh man, it's not there. Buy low and sell high, and then we can minus. So here we're getting output, which is 3, and expected, which is 7. Oh my god, I'm doing equals. We have to do plus equals. I was gonna say, I knew I was doing something right there. And boom, this is gonna run linear time in constant space. Best time to buy and sell stock, or given an array of prices where prices to buy is the price to be given. So this is the same problem as before, except you can only do one thing, right? You can only make one transaction here, and the way you can do this, right, is because you can do this with the 2-pointer pattern, right? But you can do this really fast, right, with just, I think, like 5 or 6 lines of code. So we have to do, right, because you can't time travel when you're buying stocks. You can't buy, let's say, on the second day, right, which is 1, and sell on the first day, right, which is 7. So linear iteration going forward is going to help us here. And to do that, all we have to do is just say max profit is going to be equal to 0, right? And that's important because we said return the maximum profit you can achieve from this transaction. If you cannot achieve any profit, return 0, right? So we're going to take the max of max profit, another number, right? And if our profit, right, is only negative here, as you can see, the numbers are only going down. We can't make a profit. Then we'll never be able to beat 0, right? And we're going to have to say our minimum stock, our min stock price, right, is going to have to be set to infinity, right? Because we're going to be taking the minimum of this and a number. We can never hard code a value that's going to be sufficiently large enough to actually make this guaranteed, right? So we can do let price of prices. We're going to say max min stock, right, is going to be equal to the math.min of min stock, right, or the current value, right, which is going to allow us to keep a running minimum value, right? Then on each iteration, what we're actually going to do, right, is we're actually going to take the maximum of our profit, right? So our maximum profit is either profit so far, right, or the price on this iteration, right, minus our new lowest stock, right? And so here we can just return max profit. It's going to run in linear time and constant space. So that's good. I'm going to reset this because I'm probably going to review this problem in a little bit. Oh no, I did this one already. I can't look. I've done this one already, so I try to reset the problems, right, and then do them another day. I didn't reset that. I forgot to reset that one. So given the string, determine if there's a palindrome, considering only alphanumeric characters and ignoring cases for the properties problem, we define the string as a valid palindrome. So the way you do this problem, right, it's really a standard string reversal problem, right? Standard string reversal problem with standard string reversal problems where you actually have to just use the standard string reversal algorithm, right, which is also used for reversing strings or just checking whether or not strings are the same forwards as they are backwards, right? This is typically done with a while loop, right, and it stops when the 2 pointers reach in the middle, right? To make sure, right, that we're only working with alphanumeric characters, right, we're gonna have to ensure that start points to a alphanumeric char, and ensure end points to an alphanumeric char, right? Now, if that's the case, right, then we just have to check, right, if s sub start, right, dot to lowercase, right, which is a function, does not equal s sub end, right, dot to lowercase. Why are we doing dot to lowercase? Because we have to also ignore case, right? So a has to be equivalent to little a, right? And so if these aren't equal, we're going to return false, right? If we can make it out here, we're going to return true, right? Because this is going to end when they're when the 2 pointers meet each other or they pass each other. If these aren't equal, then we're going to return false, which means if they haven't returned false, they must be equal, right? So we're going to need actually another function, right, which is going to be called is_char alpha numeric. Let me go to a function. We're just going to take one character here. This is kind of the way I decided to do this problem. We're going to do it with regex, right? So we're just going to find the start of string from a to capital Z, a to little z to 0 to 9 as our character class. I'm fumbling my typing here, and we're going to take at least one character has to exist for that, and we're going to do end the character, right? So if s.match right, then we're going to return true. Otherwise, we're going to return false, right? And so how do we ensure that start points to an alphanumeric character? Well, we're going to say, well, start is less than end, right? What we're going to do is going to say, hey, make sure, right, that char is pointing to an alphanumeric character, right? And we're going to pass in s sub start. So this while loop is going to run while char, which is start, is not an alphanumeric character, and we're going to keep going to the next index in this string until that's true. And so we're going to duplicate this, right, for the end pointer. And then we have to make sure the end pointer is actually going to be decrementing towards the center, right? Because this is a reversal algorithm, so they're going to be moving towards the center. I think this should be good. S.match.re? What am I missing here? Oh, what does it say? Can I read property match of undefined? What does that even mean? Can I read property match of undefined S? I should make this let, by the way, as well. A to Z is if S dot match, S, which is our string that we're passing in here, that match regular expression, and we're going to return true. I'm passing in, this might be a mismatch. S sub end. Oh, I think, oh my god, I messed up. That has to be n dot minus 1, I think. I think that should be good. Because I think we were out of bounds there. This is taking too long. I think, oh my god, I forgot. Oh my god, I'm trolling. And we also, I always forget this. We have to increment start and end towards the center. I always forget this, man. That's why I have to review these problems, right? Because you do it once and you mess it up, right? So I have to make sure I fix that. And so I usually add notes for problems. Make sure to decrement and increment start and end. Speedrun, but we're going to the next problem. That one's in linear space with constant time. Oh no, I forgot to refresh this one too. I can't look. This one you can do with the Xor trick, right? Because number and 0 Xor, right, is going to return the number, right? And a number and another number Xor is going to return that number. And so what you can do, right, to get the single number, right, is you can say let value equal to 0, which is just going to start at 0. And you can say for let num of nums, right? And then what you can do, let me fix the syntax here. You can just say value is going to be equal to value Xor nums. And then you can just return value. I should have reset this one, which is pretty bad. So, why is it taking so long? Did I mess up again? Value is equal to value Xor. Oh my god, I did. It's supposed to be num. I'm so cringe. So cringe. This one's in linear time and constant space. And so we're going to go to the next one. Let me make sure my timer's still going. Okay. Roman to integer. Is represented by 7 different symbols. So we're going to need a dictionary, right, to map these symbols to their correct values. And actually, there's a really cool way to do this, and I guess I'll explain it while I'm talking, but I'll call this mapping. And so we have to make sure that we just create these mappings, right? And so this is kind of just busy work. And so you need this dictionary here, right, to define whether the value of a symbol. And without the value of the symbol, and we'll never be able to tell, right, what a symbol actually exists, well, what a symbol actually maps to. So you need this dictionary. There are ways to do it without a dictionary, but they're unintuitive and don't map to other problems, I believe. So we have this mapping, right, which is going to map a symbol, right, to a value, right? And so what you can do here, right, is you can say value is going to be equal to 0, right? And there's some special cases, right, where I can be placed before V, right, to make 4 or 9, these special denominations, right? The Roman numerals are typically written from largest to smallest, right? In the special cases where you have these denominations that make special values is when you see a number that is, when you see 2 symbols, right, where a number is going from smallest to largest, right, which breaks the rule of how you write Roman numerals, right? An example here is III, right? And you write a normal number like 58 LVI from smallest to largest, and then you can see here, right, when you have something like 9, it's breaking there. We have a small number and then a large symbol, right? So to do that, we're going to do for let I is going to be equal to 0. I is going to be less than s dot length minus 1, right? Because we're going to be checking one symbol ahead, right? And I think the way we do this is if s, we're going to have to look this up in mapping. If s sub I is less than mapping sub s sub I plus 1, what we're going to do is do value minus equal mapping sub s sub I, right? Otherwise, what we're going to do is value plus equal mapping sub s sub I. Oh, we're actually going to do oh yeah, we can do s sub I plus 1 here, I think. And we should be good. The problem with this thing, I think, is that we have to make sure to add the remaining value, right? Because we're going to be ignoring the last element in the symbol right because we're doing -1 because we're checking one ahead. And so if that's the case, we're going to have to s sub s dot length -1 to add that last value. This might be wrong. I have bad intuition about this. Oh, no way. LVII, my output is 9. How is that possible? Is my mapping wrong? 5, 10, 50. Let me check real quick. 1, 5, 10, 50, 100, 500, 1000. If I is going to be equal to 0, if I, then we're going to subtract mapping sub s sub I. Else, we're going to add value plus equal mapping sub s sub equal mapping is the length of 1. I have to think. For I length not 1. So we're gonna exhaust the list by looking one character ahead. Mapping sub s sub I is going to break the rule, so we have to do value minus equal mapping sub s sub I. We're losing time on this problem, not gonna lie. Our output, let me run that again. The first one works, but our output, LVII is supposed to go as 58, but I'm getting 9 somehow. So LV, which means we should be adding. Oops. But I think this should be I, actually. I think this will still goes the correct answer here. Oh my god, I'm a god prince. Yeah, I was adding one ahead, which means we're skipping some values. But this is gonna run in linear time with constant space because we just need this dictionary to work here. And then otherwise, we're pretty good on all the other fronts. 2-pointer approach here. Be wary of off by 1 errors, and I was not wary of them. Kind of crazy. Oh my god, another problem. I forgot to reset. So given head of a linked list, determine if the linked list has a cycle in it. The cycle return true. So this is just a standard Floyd-Warshall. I think it's Floyd-Warshall cycle finding algorithm, or rabbit and turtle, right? And so how do you go about this, right? So we have to make sure, right, that if head is equal to null, right, then there's no cycle in the list, right? So we can just return false, right? Otherwise, right, we can use rabbit, which is going to be equal to head dot next, and turtle, which is going to be equal to head, right? And so while turtle does not equal rabbit, right? So this is how long this is going to run. We're going to say make sure, right, that rabbit moves twice as fast as turtle, right? And then turtle, right, is going to move quite slow. It's just going to say turtle dot next, right? And if rabbit, right, rabbit's current position equals null, right, or rabbit's next position equals null, right, then we're going to return false. So what this basically means, right, is that they're running on a track and they don't know if they're running on a track that has a finish line or a track that is a circular track, right, like a university track, right? And if this thing is said, hey, rabbit's moving twice as fast as turtle, if they're running on a circular track, then rabbit should run in the turtle. If they do, right, this case will be false, and so we can return out here and say return true. But if rabbit ever reaches a finish line, or rabbit's next step is a finish line, right, then we're going to return false. And this should work in linear time with constant space. And so I don't usually mess this one up because it makes a lot of sense. Right function, longest common prefix, right function to find the longest common prefix string amongst an array of strings. There's no common prefix for empty string. Strings is going to be equal to flower, and flight, and the output here is FL because the longest common prefix is going to be FL, right? Here we can see the longest common prefix is going to be empty because none of these characters even share the first, none of these strings even share the first same character, right? And per the problem's requirements, we're going to say if there's no common prefix, return an empty string. And so what we can do, right, is we can assume, right, that LCP is going to be string sub 0. Right, and I think there might be strings.length can be 0, so we're going to say if strings.length right, equals 0, what we're going to do is we're going to return an empty string, right? Because it says the constraints here that length can actually be equal to 0. So how do we solve this? We assume, right, that our longest common prefix is going to be equal to 0. And what we're going to do is we're going to iterate for let word of strings, right? And then for each word, right, what we're going to do is we're going to pop cars off LCP until it matches, right? Then we're going to check, right, if LCP dot length is equal to 0 here, right, then we're just going to return an empty string, right, because we exhausted it, right? Otherwise, we're going to return LCP because it's possible, right? So we're going to pop cars off LCP until it matches, right? So how do we do that? So we have to say while LCP, while the current word, right, dot substring, right, so from the 0th index, right, up until LCP dot length, right? So while that substring, right, does not equal LCP, what are we going to do? Well, we're just going to remove characters off of LCP until it does, right? So we're just going to keep cutting characters off LCP, right, until it is a substring, right? And so we should be good here, and we can return true. And so it's going to run in linear time with constant space. Let me remove this. I leave the notes because when I review much slower, and so I have to make sure that I'm constantly, that actually does not run in linear time, that previous question. That's actually going to run in O of S time because our operations are going to be linked to how many, no, that actually runs in of N by L because where N is the number of words in the string array, right? We're going to have to produce, we're going to have to, no. That is actually O of S. Yeah, it's going to be the sum. I don't know. I have to double check that. That's how it be sometimes. Intersection of two linked lists. Right? We're going to find the node at which the intersection of two singly linked lists begins. For example, the following two linked lists begin to intersect at node C1. So there's actually a cool way you can do this, right? So quick synopsis, right? So if you're looking at these two lists, right, you're like, wow, how do you know if their two linked lists are having an intersection, right? So what you can do, right, is you can look for, there's no possible one, right? But if you imagine this example right here, right, and imagine that B1 didn't exist, if you can iterate both of these pointers, right, simultaneously and just check if they're the same, then you'll know that this is the first one that they intersect at, right? So the problem just becomes, right, having to make sure that the runway before they intersect is the same. And so how would you do that, right? So we just have to get the length of A and B, right? And then what we're going to do, right, is we're going to increment the longest list by the abs of len A minus len B, and then from there iterate through both linked lists simultaneously, right? And then that's going to be how we do that, right? So let's create some temporary variables here. We're going to call head 1 head A, and then we're going to call let head 2 equal to head B, right? We're also going to need A len is going to be equal to 0 and let B len also equal to 0. And what we're going to do is while head 1 does not equal null, we're going to increment head 1. Head 1 is going to be equal to head 1 dot next, right? And on each iteration, right, if that exists, we're just going to add 1 to head len ren. And then we can do the same thing for head 2 here. While head 2 does not equal null, B len is going to be equal to B len plus 1, head 2 dot next. So now we have the lengths, right? And so what we need to do is we need to increment the longest list by the absolute value of length of A minus length B, right? So first we have to figure out which list is the longest, right? And so we can do that by saying, hey, if A len, right, is greater than B len, then longest list is actually going to point to head A. Otherwise, it's going to point to head B, right? And so shortest is going to be, hey, if longest, right, equals head A, right, then shortest must be head B. Otherwise, it's going to have to be head A, right? And so here we can increment the longest list by the absolute value of len A minus B. And so to do that, we can do for let I is equal to 0. I is less than math.abs of A len minus B len, right? I plus plus. And then we're only going to increment longest, right, that many times. Right here, now, right, we can just iterate, right, while longest does not equal null and shortest does not equal null, right? What we'll do is we'll just say, hey, if longest equals shortest, right, then we're just going to return true, right? I mean, we're just going to return longest, right? Because we have to return the node where they first intersect, right? Otherwise, if we made it to the end of the list, right, we never actually were the same, right? Then we're just going to return, what do they want us to return in that case? I don't even know. I think we're just supposed to return null. I haven't done this one in JavaScript before, so let's see if this works. I think we're forgetting something. Yep, I forgot to increment longest and shortest. Shortest equal shortest dot next, and this, our timelet's going to exceed soon, and this is good. So yeah, so this runs in O of m plus n time, right, where m is the length of head A and n is the length of head B, right? Our space complexity is going to be constant space, and so that's a pretty cool solution. That's actually not included in the solution bar here. Okay, so we're at min stack. Min stack is really easy. Design a stack that's where it's push pop top and retrieving the minimum element in constant time, push element x on the stack. So you actually get push pop and top for free depending on the underlying data structure you use to store the elements, right? We're going to use an array. So push is actually going to be in an array list constant time amortized, and pop and top you're going to get for free because you can instantly calculate the end of an array in most languages, right? And so what we're going to do, right, is we're going to say this dot stack is going to be equal to 0 empty list, and this dot min value is going to be equal to an empty list, and min value is we're going to use to get min value in constant time, right? And so this is actually in the wrong spot. This should be in the constructor. And so we're going to say, right, hey, if this dot stack dot length, right, is equal to 0, right, then how do we make sure that get min and push are constant time, right? So if our stack is empty, right, then we don't actually have to think about how we're going to add to get min, right? We're just going to say this dot stack dot push dot x, right? And since there's no other elements, right, in the stack, and these are parallel stacks, right, then we can just push x on to min value as well, right? If the stack isn't empty, right, then stack dot push dot x is going to be the same, because no matter what element we add to the stack, we're just going to add it to the top of the stack. But for min value, however, to make sure that min value actually represents the global minimum at the time of addition for this element, right, we have to make sure, right, that when we add min value, right, we're taking the min of the last element that we added to min value, right, minus 1, and element x, right? And so that will make sure that whenever we pop an element off the stack and it's min value, right, the next element off the parallel stacks is also going to be the minimum, right? So for pop, it's going to be the same, right? If this dot stack dot length does not equal 0, right, then we're actually just going to remove this dot stack dot pop and this dot stack, this dot min value dot pop, right? For top, it's going to be the same, right? If this dot stack dot length, right, equals 0, which means the stack is empty, right? What are we going to show the person, right? We're just going to show them 0, right? And that's a good question to ask in an interview probably, because this doesn't say what to return when the stack is empty. Otherwise, we're just going to return this dot stack sub this dot stack dot length minus 1, right? And for get min, now this, what we've done in the beginning with with push, has ensured, right, that get min is going to be very simple, right? And so since these are parallel stacks, we can just check if this dot stack dot length is empty. It's going to also be the same if min value is empty, because they're parallel stacks, right? And so we're just going to return 0 if the stack is empty, right? I guess that's bad styling since I didn't use curly braces before. And so else, we're just going to return this dot min value, right, sub this dot min value dot length minus 1. And this one, I don't usually mess this one up, and I messed it up. It usually does. Oh no, I didn't mess it up. Hey, so all the operations here have to work in constant time, right? Or you actually can submit it without constant time, but this is actually constant time, and it's also going to be linear space, right? And so that is min stack. I'm going to reset this one. So given a column title as appeared in Excel sheet, return its corresponding column number. A maps to 1, B maps to 2, C maps to 3, Z maps to 26, AA equals maps 27. So what you can see in this one is that if you take a look at this one, right, A to Z, right, is actually just code for base 26. Base 26. So what they just want us to do, right, is actually we can just calculate the value, right, as if this was base 10, base 16, if it was hex, if it was binary, so it's not really going to matter, right? We have to make sure, right, that we're iterating over, let I is going to be equal to s dot length minus 1, so we have to iterate through the string in reverse order, right, because powers in numbers and bases, right, and any number pretty much start at 0, right? You can start from the front, but I don't know, that's kind of hard, and that's not what we're doing here. And then while I is greater than or equal to 0, I minus, right? And so we're going to say, right, is that So we're gonna need the our letter value, right? Actually, don't know how to get. Oh no, I think we can do. So we can do s sub I, right? Dot car code at 0 minus 64. I think will give us the letter value, right? And so to calculate the value, right, what you're gonna do is just gonna take the letter value, right, which is gonna be an integer, right? You're gonna multiply it, right, by the base, which is 26, right, to the power, right? And then you can just do power plus equal 1, and then you can return the value. So hopefully this works. That works perfectly, and so that's pretty dope. This runs in linear time and constant space, where n is the number of characters in the string that they want us to Provide a function that takes the unsigned integer and returns a number of 1 bits. It has, also known as the Hamming weight. I don't know if I've done this problem before, to be honest. Follow up: if this function is called many times, how would you optimize it? Input string must be a binary string of length 32. Okay, if that's the case, then I think you can do Hamming weight is going to be equal to 0, and then we can do we're just going to make sure that this loop runs 32 times. I'm going to be honest, I don't even know. I++, and then we're just going to do, this is similar to reverse bits, I think. We're just going to say if n and 1s, we're just going to check if the last least significant bit is 1, right? And if it is, we're just going to do Hamming weight plus equal 1, and then we're going to shift n to the right 1 bit, and I think we can return Hamming weight. I hope this works. I think I have done this problem, but I haven't done it in a long time. Submit. Okay, that's pretty dope. So this is going to run in constant time. Why? Because no matter the input, and they're guaranteeing that our input is going to be at least 32 bits, we can process any number in 32 operations. So this is going to be constant time, and then constant space as well. Make a note similar to reverse bits. So, okay, given an array nums of size n, return the majority element. The majority element appears more than n over 2 times. There's a few different ways to do this, depending on if you want to lean towards more space or time. I'm going to lean more towards time here, so this is going to be done in linear time. To do this, we're going to create a dictionary, and then we're just going to iterate for let num of nums, right? And we're just going to say if num in num dict, right? The num dict sub num is going to equal to num dict sub num plus 1, right? Else, right, we're going to add it to the dictionary for the first time. Its value is going to be 1, right? From there, right, you can do for let key in num dict, right? And then what you can do there is just say, hey, for num dict sub key, right? If it's greater than nums.length over 2, right, then just return the key, right? Otherwise, return. Well, I think this is guaranteed. Okay, it always exists in the array, so this is never going to call the return 0. We're just going to put it in anyway. And so this is actually going to be in linear time with linear space, right? Because we're creating a dictionary, which is going to scale linearly with our input to the function, which is going to be in where n is number of numbers or elements in this array right here. So I'm going to reset this so next time I do it, I haven't seen it. Oh god, I forgot to reset this one. I have to block it. Reverse bits of a given 32 bits unsigned integer. So it's going to be like Hamming weight. We're also going to get 32 bits here. And so we can call rev equals 0, I think. And then we're going to make sure that this runs 32 times, right? And then what we're going to do is we're going to shift rev over 1 bit to make space for what we're about to do. And we're going to say, hey, if n and 1, which means there's an the least significant bit in n right now is 1. What we're going to do is going to add 1 to rev, right? And then we're going to shift n right 1 bit, right, to move it so we can copy its next bit on the next iteration. And then we can return rev. But I think in JavaScript there's a weird thing you have to do here. I think there's a weird thing you have to do here because the numbers don't process correctly. There is. I think what you have to do is, I think you have to do this or something like that. Oh man, there's something weird you have to do in JavaScript. I don't remember what it is. because you can't regularly I think something happens when you shift the bit over one. When you shift the bit over one, did I just try this? Did I just try making this the second power? Oh wait, let's try. No. Oh man, there's some weird JavaScript problem here, right? Because our number gets cast to, I think, a different number of bits, and so this is why it turns out really weird here. I had this problem before, but I forgot how I fixed it, man. Rev plus equal 1? Okay, I think actually you can just move it to the right. You have to move it to the left by 1 bit, and then we're gonna put this in here, and then we're gonna do rev is equal to rev to the second power. I think it's something like that. Oh, I don't remember. It's some weird JavaScript problem. I don't remember. It's some weird. You know, just for the sake, I don't know how to fix the problem with JavaScript, but we're just gonna do it in Python because I don't remember. Rev is gonna be equal to 0, right? And we're gonna say for blank in range, right, of 32. We're going to shift rev over 1 bit. Oops, I'm still in JavaScript mode, right? And then we're gonna do if and 1, right? Then we're gonna add 1 to rev, and then we're gonna shift n to the right 1 bit, right, to move to the next bit that we want to copy. And then we're just gonna return rev. I think this should work. What? This one doesn't work either? No. Oh wait, I think I'm, oh my god, I think I'm using the wrong operator. No way. I think I was literally using the wrong operator. Now I'm going to try this in JavaScript. Better not work. No. No. Okay. We're back. And then I think you can do this right here. Okay, maybe you can't do that. Yeah, it's still, the JavaScript problem still remains. Yeah, the JavaScript problem still remains, right? But we solved it in Python, so that's good enough for me. This runs in constant time as well, since we're always going to have 32 bits, right? And so we're always going to do 32 operations to solve this. So this is going to be constant time and constant space. So right now we're going to determine if a number n is happy. Happy number is a number that is defined by the following process. Start with any positive integer, replace with them. So we have to linearly summate the squares here, right? And we have to keep continually linearly summating the squares until we get to 1, right? So we're going to have a while loop, right? That's going to say while some value, right, does not equal 1, right? And then if that value ever equals 1, right, we'll get out of here, so we'll return true. So we must have some value in here, right, that's going to return false. Right, and so there's a couple things that can happen. Repeat the process. So this can loop endlessly, right? So we're going to need a numdict. Actually, we're not even a numdict. We're just going to need a numset. I think you can do this for a set in JavaScript. I'm going to be honest, I don't even know. I'm actually getting hard capped by not knowing what I can and can't do, or the proper syntax for stuff in JavaScript is. So, so here we're going to have to. So we can just do while n does not equal 0, right? So we're just going to linearly summate squares. Right, then we're gonna update n with summation, add to dict, right? Check if in dict. If so, yeah, if it's in the dictionary, we're gonna return false, right? Else, add to the dictionary, right? So we should be good here. So to linearly summate the squares, right? So we have to, so we can do for let I is equal to n dot toString dot length. Oh no, we only need this to run 4 times. Okay. So we can do for I is equal to 0 while I is less than n dot toString dot length. So we need to, for this loop to run n dot toString length times, right? And then to linearly summate the squares, right, our digit is going to be equal to n mod 10, which is going to rip off the last digit of the number. And so we can say our value here, or our let summation, is going to equal to 0. We're going to say summation is going to be plus equal digit, right, to the second power, which is good. And then we have to update n, right, by doing n divided the, I guess, the int of n divided by 10 to rip off the last value of n and keep it that way, right? Then here we're going to update n with the summation, right? And then we're going to say, hey, if n, if n in num set, right? Then we're just going to return false. Else, right? Then we're just going to say num set dot add n. I think this should be good. And that's good. It's not looking good here, boys. It's not looking good. It's taking too long. I think time limit exceeded. I think it might be the set. I don't know if I'm using the set properly. Last executed input was 2. So I don't think we're actually properly exiting here. If n in num set, I'm just going to change this to a dictionary. This is a speed run, and I don't know. We're just going to do num set sub n is equal to 1. 3 output is true, while n does not equal 1. If n in num set, n is going to be equal to the summation. We want 10 to the last, and then summation n is equal to summation. If n in num set, add it to the dictionary. Something strange is happening here. While n does not equal 1. Input 3, so n dot toString dot length I plus plus. Oh, 10 to get the last digit. Digit squared. Update n with summation. Then we're gonna check if I think our input is 3. I wonder why that's failing. I is less than n dot toString dot length I plus plus n mod 10. It's gonna be plus equal digit to the second power. N is gonna be equal to parse int, turning it into an integer here, ripping off the value at the end. N is going to be equal to the summation now. Check if it's in the dictionary. If n in num set, return false. Else, we're going to add it to the dictionary. I wonder why this is failing. Loops endlessly in the cycle, which does not include 1. Those numbers which this process ends in 1 are happier. And false if not, while n does not equal 1. Turn false. Wait, why can't you place n dot to? Oh my god, I figured this. I ran into this problem before. Oh my god, I ran into this problem before. I forgot. This is a JavaScript problem. I always run into these nonsense problems. Watch us fix it. Boom. Right, so the problem here, right, is that I think this loop is, whenever it's interpreted, right, this value actually updates each time. And so as we're ripping off values with n divided by 10, our number of iterations is actually decreasing in time. So we need this to be set prehand before the loop. That's why they're having so much trouble figuring out. This is going to be done in it's going to be like in log of n time, actually, I believe. Yeah, it's going to be done in log of n time. And our space complexity is also going to be log of n. Next problem. Oh god, I saw this one as well. Given a string s, you know what? Just to skip that one, we're just going to randomly kick a tab in the middle. Given an integer n, return true if it is a power of 3. Otherwise, return false. Integer n is a power of 3 if there exists an integer x. So basically, we have to determine whether or not, given an integer n, if it's a power of 3, right? So to do this, right, you can literally just say, we can literally just generate all powers of 3, right? And if we ever pass a number, right, then A, sucks to suck, right? And so we're going to say while let value, right, which is going to be equal to 0. And then just before we even start the loop, we're going to say if n is equal to 0, right, we're just going to return false because the lowest number of a power of 3 can have is 3, right? So 3 to the 0, I believe, is 1, right? So n is equal to 0, it'll never be a thing, right? So all value does not equal n. Right, what we're going to do is we're going to say value is going to be equal to value is going to be no. Value is going to be equal to 3 to the power, right? And so if value is greater than n, right, what we're going to do is we're going to return false, right, because that means we passed it, right? Otherwise, right, if we escape this treachery, we're going to return true because it is a power of 3. I think I forgot to increment power here. I did. So we're actually going to get a time limit exceeded. We get our time back. We get our time back. Oh my god, this takes forever. I might just go to another one. Okay, so that's good. This runs in linear time, worst case complex. You can actually do this in log in time with division, but this is the solution that I'm working with now. I'm slowly making it better. That's power of 3, constant space as well. So implement stir. Return the index of the first occurrence of needle in haystack, or -1 is if needle is not part of haystack. For the purpose of the problem, we'll return 0 when needle is empty string. So it's going to say, hey, if needle.length as per the problem's requirements, right, if it's equal to 0, we're just going to return an empty string, right? Otherwise, we have to check whether or not our needle exists within the haystack, right? To do that, what we can do is just iterate through the list while haystack.length, right, I++, and we're just going to check whether or not this value, right, exists at each index. So we can just say, hey, if haystack.substring, right, at the 0th index all the way up until needle.length, right, if they're equal, right, to the needle, then we're going to return I, right, because that would be the index that we found this solution at, right? Otherwise, right, we're going to return -1, it says to return when you can't find the number, because if we make it out of this loop without ever returning an index, it means that the needle does not exist in the haystack, right? So our output was no, what is going on? I think my page just reset. Wait, what is going on? Okay, it came back anyway. So we're gonna return I to needle.length haystack.substring sub. Oh, that's my bad. We're actually going to start at I. Wait, what? Oh no, I plus needle length. So our substring here is going to be from a start index to an end index. So it has to be a start index plus our start index plus the needle length. So this is going to run an n by l time, right? Because for each iteration, right, for our entire loop, we're going to have to run n times, where n is the number of characters in haystack, right? On each iteration, right, we're doing a linear string comparison, right, which is going to be based off of the length of the needle, right? Because we're also going to be checking needle length and needle, right? So it's going to run on each iteration, we're going to run n times, right? And on each iteration, we have to do l operations, so it's going to be on n by l. Given an array nums, write a function with all zeros at the end of it while maintaining the relative order of the non-zero elements. So this you can do with the sliding window pattern, right? So what you can do is you can say for let I is, we're going to do for window end is equal to 0. Window end is less than nums.length. Window end plus plus, right? So what are we going to do here, right? We're going to say, hey, if nums sub window end, right, is equal to, if nums sub window end is equal to it does not equal 0, right, what we're going to do is we're actually going to swap it with, and we're going to keep track of our window start here, we're going to swap it with our window start. So we're going to say let temp equal to nums sub window end, which is 0. And so nums sub window end is going to equal to 0. Nums sub window start is going to be equal to temp. And then we have to move window start up by 1, I believe. And then we don't have to return anything. I think this should be good. Okay, that's good. And so the idea here, right, is that we're iterating through the array. Each time we run into a number that's non-zero, we're just going to throw it over us, right? And so we're going to have to keep this thing going, or we're going like this. And at the end, all the zeros will be moved to the end, right? Review, sliding window pattern plus dynamic. I have to review that later. Okay, remove duplicates from sorted array. Given a sorted array nums, move the duplicates in place such each element appears only once and returns a new length. So this one you can actually do, right, with remove the duplicates. So we're not returning anything because we're supposed to be modifying nums in place, but it's already sorted. So we're just going to use the pointer double pointer pattern, right? And so before we even do, two pointer pattern, before we even do that, right? It's the 2 pointers, right? One has to start in front of the other, right? Otherwise they both start at the same value, which would mean we remove the first element, which doesn't make any sense. So if num length, right, is less than or equal to 1, right, we're just going to return what do we return? What does it want us to do? It returns a new length. So we're just going to return nums.length, right? Why? Because if an array has 0 elements, right, there's no duplicates, there's no elements. If an array only has 1 element, there's no duplicates, there's only 1 element, right? And so here we can say while p1 is remove duplicates. The pointer, how many steps should p1 if no duplicates are detected? Right, so this is going to run while p1 is less than nums.length, I believe, right? And so the idea there is, yes, while length minus 1. And so we should be good there, right? So if nums sub p1, right? Oh no, let end equal to nums.length. Now remember, minus 1. Right, because we're going to be moving elements from the array during this while loop, and so our end is going to be a moving target, right? So if nums1 is equal to nums2, right, what we're going to do is we're going to nums1 sub p1, right? Nums.pop at p1, right? So we're just going to remove that index there, right? And then we're going to decrement end by 1, right? Because we removed an element from the array, and so we have to make sure, right, that we're never going out of bounds, right? Otherwise, if there's no elements to remove, right, we're just going to increment p1 by 1 and p2 by 1. I don't know if you can do pop in JavaScript, but we'll see. And then we're going to return nums.length. Oh, you can't do pop in JavaScript. Wait, maybe you can. No, I don't think you can do pop in JavaScript. I think you can do splice. Splice p1. Oh man, I don't know how to remove an element from an array in JavaScript. I'm so cheeks. Oh man, I don't know, bro. I think it's, do you have to do nums equal to nums.splice p1? I think you do p1 and say you just want to remove 1 element. There you go. Boom, there you go. So what's the time space complexity? This is going to be run in linear time, right, worst case, and our space is going to be constant space complexity. Removing an element from the array, the worst case is linear time though, so any percent, am I right? We're almost at the end here. So missing number. Given an array nums containing n distinct numbers in the range 0 to n, return the only number in the range that's missing. This is kind of a cool problem. So there's only n distinct numbers in the range 0 to n, right? So when you have 10, right, you're actually missing 11 numbers because you have to have 1 to 11, right, and then including 0, right? So it's going to be 11 numbers. But since only 1 number is missing in a distinct range, you can actually use the Gauss formula to instantly calculate the value, right? And that's actually just length of nums, right, times length of nums plus 1, and then you just wrap the whole thing and divide by 2, right? And then from here you can just say, hey, for let num of nums, right, and just do Gauss minus equal num, then you can just return Gauss, right? Because it's a linear summation of distinct values, right? And if you subtract this array, which is only missing 1 number, you should have the number that is missing from these difference. I knew something was right here. I just did it in Python style, I think. Nums.length. Oh my god. Unexpected token, bro. What is this, bro? I do have an unexpected. What is going on, man? Boom. And there you go. This is actually linear space and constant time because the Gauss formula is pretty pog. So given 2 strings s and t, write a function in terms of t is an anagram of s. So an anagram is a string that can be arranged to form another string, right? To do this, right, you're going to have to create a mapping, right? And what we're just going to do, right, is say, we're going to say for let car car of s, right? If car in mapping, right? Then we're going to say mapping sub car is equal to mapping sub car plus 1. So here we're just creating a mapping, right, of letters to occurrences, right? And so if we haven't seen the letter, we're just going to set it to 0 because it's the first time, right? On the second iteration, right, we can say let car of t, right, iterate through that. What we'll do is we'll say, hey, if car, right, is in mapping, right, and mapping sub car, right, is greater than 0, right, what we'll do, right, is we'll decrement mapping sub car, right, minus 1, right? And so if it's never not in car, right, or we've decremented our occurrences so many times, which means we have a mismatch, right, we can just return false, right? If we make it out here, we can just return true. And before any of this starts, right, if s.length, right, does not equal t.length, right, then they're not anagrams, right? If they're not even the same, length, they're not anagrams. So you can return true here. This is going to be linear, O of m plus n, or s plus t, right, where s is the length of s, number of characters in s, and t is the length of number of characters in t. And our space complexity, right, can be the length of s or t, right? So if you wanted, you could only use a dictionary, right, that has the smallest, for storing the smallest word here, right, or the smallest string of characters. But we're not doing that. We're just going to take the smallest. We're just going to always assume, right, that we're just going to take s. So boom. Right. Oh my god. Okay, there's nothing here. Write a function. Am I still recording? Okay. Write a function deleted node in a single linked list. You will not be given access to node deleted. So you can actually do this in constant time, right? And this, to do this, right, you just need to say, you just need to copy the value of the you just need to copy the subsequent value, like the following node, right, and then route your next pointer, right, around the next node, right, around the duplicated node, thus deleting it. And so this is going to run constant time, constant space, right? It's 2 lines of code. I don't usually mess this one up. Oh my god, I saw this one already. I'm just going to reset it and choose a different problem. Given an integer array nums, find the contiguous subarray containing at least one number which has the largest sum and return its sum. Interesting. Given an integer array nums, find the contiguous subarray containing at least one number which has the largest sum and return its sum. This is definitely sliding window pattern, but so we can say let max sum, right, equal to -infinity, right? And then what we're going to do is we're going to iterate for let num of nums, right? And we're going to say current sum is going to be equal to 0. Current sum is going to be equal to current sum, right? Or, you know, to make it even more literal, we're going to say window sum, right? Window sum, right? Plus equal num, right? And what we're going to say is we're going to say, hey, right, if window sum, right, is actually less than num, so we just added this number to our window sum, right? So let's just say our window sum is -2 and our number is 1. We just added 1 to it, right? So if our window sum, which we just added this newfound number to, is still less than num, right, then why even care about our window sum anymore, right? Just change it to num, right? And then on each iteration, we're going to say our max sum is equal to the math.max of max sum, right, and window sum. And I think we should be good here to return max sum. Dope. So this is going to run in linear time and constant space. You're climbing a staircase that takes n steps to reach the top. Either you can climb 1 or 2 steps, and how many distinct ways can you climb to the top? So actually, this is a dynamic programming problem with you can actually optimize with memoization. And so in this approach, I think we're going to do top down because it's just simpler to do. And so what we'll do, right, is just going to say return climb of n, right? And then up here, we're just going to define this climb stairs function, which actually I think we're going to need a few more variables for memoization, which is going to be a dictionary. We're going to pass in memo and n, which is dope. And so we're going to say we're going to take n and a memo, which is an array, right? Oops, and my syntax is kind of bonky right now, right? And so how do we climb the stairs properly, right? So there's a few cases we have to check first, right? So if n, or actually I might as well change this to I because we're passing in n, right? So if I, right, so we're going top down, so we're just going to say, hey, we're just actually supposed to be climbing a staircase, right? We're just going to flip the problem on its head and say, hey, we're actually starting at the step of n. We want to get to the bottom staircase, right? How many different ways can you do that? The problem's symmetrical because you can do it either way, right? And so we're going to say, hey, if n, right, equals, I mean, if I equals 0, right, it means, hey, you properly reached the end of this, you properly reached the end staircase, right? So that's a possible way, return 1. Right? And then we're going to say, well, okay, I see what's going on there, right? So we're going to do else if, right? And then we're going to say, hey, if I is actually less than 0, right? That means we got to a negative step, right? It means we went too far, right? And so if that's the case, right, just return 0, right? Just don't even bother it, right? And obviously, if we're before 0, right, we're not going to do anything, right? And so the other thing, right, we're going to do is we're going to say, hey, else if, right, if I is in memo, right, then just return memo sub I. We calculated this value already, right? So why even try and calculate it again when we know the value already? And then, right, so if none of those things are true, right, which means we've never climbed from this step before, right? And so to optimize this problem, what we're going to do is we're going to say, hey, climb from my current step, right, take 1 step and take 2 steps, right? So we're going to say I minus 1 and pass in memo, right, plus climb of I minus 2 and pass in memo, right? And we're just going to return memo sub I. I don't usually have a problem with this problem, so hopefully it works. There we go. And so the time complexity here actually goes from, with memoization, goes from 2 to the n, right? Because each node in the binary tree is going to have 2 children, and we're going to be doing a lot of redundant calculations. It actually reduces to n, right, where n is the depth of the tree, right, where each depth of the tree signifies a new step. And so if we've calculated a step before, right, then once we've reached the depth, we don't have to calculate that value again, right? So we're actually going to, this problem is going to, operation-wise, time complexity-wise, is going to revolve around how many steps we actually have to do. Space complexity is going to be linear space, right, because we're using recursion here, and each iteration we're going to add a layer to the recursive. We're going to add a stack frame to the runtime stack. Given a non-empty array of decimal digits returning non-negative integer, we'll increment 1 to the integer just stored just away. So this problem, right, we're given an integer decimal number, right, which is just represented as an array, right, and so we have to add 1, right, to this array. Seems simple, right? 123 to 124, right? But then you have, if you have a 9 at the end, right, what do you do? Because when you're adding 1 to a number, if you have like 999, you have to probably get the 9 like 3 times, right? And then you have to add 1 to the front. So how do you go about this, right? So what we can do, right, is we can iterate, right, for let I, or for let index equal to 0, I, or index is less than digits dot length. And actually, yeah, I'm actually trolling here because we actually do this in reverse, right? Because when you're adding from a number, you don't add from the thousands place, right? You add from the ones place. And so the last index in an array, right, is digits dot length minus 1. And we're going to run right while index is greater than or equal to 0, and then index minus minus, right? So what we're going to do, right, we're going to say, hey, if digits sub index, right, equals 9, right, then turn it to a 0, right? Because if you're adding 9, if you're adding 1 to 9, right, what does it equal? 10, right? So you turn actually 9 to a 0, right? Otherwise, right, what you're going to say, this actually does not look clean without the curly brackets, but whatever. Else, right, our number is non-9. So if our number is non-9, what do? You just say, hey, digits sub index, right, is equal to digits sub index plus 1. It's like if you're adding 1 to 14. Our number, which is 4, which is our least significant number, is 4. Add 1 to it, number is 15, right? Then we can return digits, right? Otherwise, if we make it out here, right, what does that mean? We only exit here, right, if we ever reach a non-9 number. So what do you do if you have 99999? Well, we turn it all to zeros, right? What do you do when that happens, right? You have to do digits.unshift 1. Why? Because we turn all these to zeros, right? When you add 1 to 9,999, you get 10,000, right? And so you can return digits. So I think this should be good. I forgot to remove this line. Dope. So this runs in linear time, right, where n is the number of digits in this array. It's often going to be far less than that, but it is what it is. Wait, am I still recording? Okay, pog. Okay, given a string, find the first non-repeating character in it and return its index. So we just have to find the first unique string, right? So to do this, you can just create ldict, right, which is just going to be equal to a dictionary, right? We're just going to say for let car of s, right, if car in ldict, right, what are we going to do? We're going to say ldict sub car is equal to ldict sub car plus 1. So here we're just creating a linear mapping, right, of letters to occurrences. If the first time we see it, we're just going to say it equals to 1. Then we're gonna iterate, right? For let key, right? Is it of or in? For let key of ldict? I don't know, right? We're just gonna say if l subdict, right, sub key, right, equals 1, right? Then we're just gonna return that key. And if it doesn't exist, right, so if we make it out here, we're just gonna return -1. I think this works. Okay, I think it's in. What? Output is non? For let key. I think it's of. I think it is of. ldict is not iterable. Key of ldict. For let key of ldict sub key equals 1. Oh man, syntax woes once again. Actually, I think for let key of ldict is not iterable. Bro, I don't remember the syntax for this, man. For let ldict is equal to a dictionary or just an object, really. For let key of ldict. If key in ldict do I have to make, does it have to be var there? I don't understand. ldict is not iterable. Oh man, ldict is not iterable. JavaScript iterate dictionary. I don't know what the syntax is, man. I don't know what the syntax is for var key and dictionary. Okay, so it's just wrong. I think it's just literally in. My output is non. Why is my output non? Return key. If let car of s, ldict sub car. Let car of s sub car. Car is equal to 1. Let car of s, if car and ldict. Alright, else ldict sub car. Wait, I'm so confused. I'm not sure why this isn't working. My brain might be fried, actually. My output is non. Somehow my output is non. Expected 0. For let car of s, our input is s. Car in, if car is in ldict, which is up here, ldict is equal to ldict sub car plus 1. Otherwise, ldict sub car is equal to 1. We're adding it for the first time. For let car in ldict, if car is in ldict and ldict sub car is equal to 1, return car. Oh my god, I'm trolling. I'm supposed to return the index. What am I doing? I'm supposed to return the index. If I'm returning the index, now how would I change my solution? If I was returning the index, so for let car in ldict, for let car in s, if car in ldict and ldict sub car is equals 1, we just return car. Oh no, we return not car. We would just return for let I is equal to 0, I is less than s dot length, I plus plus. And then instead of car, I think I can literally just remove this entire case on the side here. We'll just say s sub I, and then here I can just return I. I think that was a one-head move of me. I think these problems are just fusing together in my head. So there's going to be linear space and linear time. The problems are fusing in me head. Oh, I saw this one already. I'm just going to clear the screen and go to a different problem. So here we have to merge two sorted integer arrays, nums1 and nums2, merge num2 into nums1. Nums1 array has enough allocated space, right, such that it has enough space for nums2, right? So the actual space in nums1 is m plus n, right? So there's 6 indexes available. M is and n represent the number of initialized elements in num1 and nums2, right? So how do we do this, right? So we can actually go and copy the elements, right? For let I is equal to 0. Right, I is less than m, I plus plus, right, and we're just going to do copy dot push nums1 sub I. So we're just going to copy these elements in the elements in nums1, right, up to index m, right, and then what we're going to do is, right, we're going to try to exhaust both lists, right, and to do that, what we're going to do is we're going to say while, we're also going to need 2 pointers here, while p1 is equal to 0 and let p2 is equal to 0. These are actually going to be read pointers for nums1 and nums2, and then we're going to have a write pointer, right, so while p1 is less than m, and while p2 is less than n, what we're going to do is we're going to say write plus equals 1, right, which is always going to be, we're always going to be at most is going to run write times, right, because this is going to run while p1 is less than m and n, right, so we'll never go out of bounds, right, and so we're going to say is if copy sub p1, right, is less than nums2 sub p2, what does that mean, right, so that means that p1 is less than p2, right, so that means that we should, in nums1, in the right index, right, we should write copy sub p1, and then we're going to increment p1's write pointer by 1, right, otherwise, right, it's going to mean that p2 is smaller, so we're going to do the inverse, right, nums2 is going to be equal to p2 plus equal 1, right. After out here, right, we guarantee, right, that at least one of the lists has been exhausted completely, right. How do we know that? Because this only runs while both of them have elements, right, so when this stops, only one of them will still have elements remaining, right. So how do we make sure that we find those remaining elements in? We say while p1 is less than m, right, so if p1 was a list that wasn't exhausted, it won't equal m, right, so if it does, we can say nums1 sub write is equal to copy sub p1, right, and then we can just increment write plus equals 1 and p1 plus equals 1. We can do the same for p2, right, and we don't actually have to worry about the fact that there's 2 while loops here, right, because one of these lists is for sure exhausted. And do p2 plus equal 1, and so I think this should be good. I think we're supposed to return something. Copy.push nums1 sub I. Boom. So this is going to run an O of m plus n time, right? And then our space is actually going to be O of m, right? Since we're copying elements up to m into a separate array to make the copying part easier, right? And so I'm just going to remove all this nonsense. So the next time I do it fresh. We're going to remove that. So given 2 arrays, write a function to compute their intersection, right? So here we have 1, 2, 2, 1, 2, 2, right? And these arrays are not the traditional set theory definition of intersection, right? So duplicates are possible here. To do that, right, we're just going to create a dictionary, right, called ndict is going to be equal to empty dictionary. We're going to say for let num of nums1, right? I'm going to say, you know how it goes, my dudes, if num in ndict, right? Then we're going to say ndict sub num is equal to ndict sub num plus 1. Right, if it doesn't exist, right, we're just going to say ndict sub num is equal to 1, right? So we're creating a linear mapping here of numbers to occurrences, right? So when we're iterating, right, through num of nums2, right, what do we do? So we're going to say, right, if num, right, is in ndict, right, and ndict sub num is greater than 0, right, what are we going to do? Right, we're going to create an array, right, which is going to be called answer. We're going to say answer dot push num, right? They don't care what order we get the answers in, right? But we have to make sure, right, to decrement num, right? Why are we doing that, right? Because we have to make sure, right, that if there's 2 2s in the first array and 3 2s in the second array, the intersection is just 2 2s, right? It's not going to be 3 2s. And so, boom, then we can just return answer. Oh, the answer's wrong. My output's 2 2. The expected was 2. Oh no. Okay, they just want I see. So they just want, oh, this is the actual set definition. So there's actually no duplicates here. So we can just change one line, I think, and it'll be fine. So that's good. So this is going to run in linear, no, it's going to run in O of m plus n time, right? Because we're iterating over both these lists. And then our space complexity is going to be O of n, or we're going to say O of m for the first element in here. But if you really wanted to be stickler on space, right, you could just take the length, only store the dictionary with the list of the smallest size. Right. And so here, write a function that reverses a string. I'm not even going to finish reading the problem for this because reversing a string is a very standard algorithm. -1, we're just going to say let's start end, right, and then we're going to say let temp equal to s sub start, right, and then we're going to say s sub start, right, is equal to s sub end, and then we're going to say s sub end is equal to temp, right, and we're going to say start plus equal 1, end minus equal 1, and then I don't think we have to return anything. Boom, that runs in linear time, constant space. Given a single link to determine if it's a palindrome, you can do this with a stack. Right, we're going to add elements to the stack, right? And everyone, you know, when you pop elements off the stack, you're going to get them in reverse, right? So what we're going to do is we're just going to say let temp equal to head. So we're going to iterate through the list once, right? Just to make sure, right, that we add elements to the stack. So temp is going to be equal to temp.next, right? And then we're going to say stack.push temp.val, right? And then we're going to say, hey, set temp back to head, right? Because now we need to make sure that this is a palindrome, right? And so we're going to duplicate this while loop again, right? And then we're just going to say temp is equal to temp dot next, right? And then we're going to say, hey, if temp dot val, right, does not equal stack dot pop, right? This ain't no palindrome, so we just return false. If you make it through, right, and return true, this is a palindrome. Something's wrong here. Stack.pop. Pretty sure I didn't actually call the function. There we go. I was 1000% sure that was right. So this is actually going to run in linear time. We're just iterating through the list once, right? And it's also going to run in linear space because we're creating a stack, right? Which is going to scale linearly with how many nodes there are on the linked list. Merge two sorted linked lists together, return to the sorted list. List should be made by splicing together nodes of the first two lists. So this is very similar to the merging sorted arrays part, right? And so how do you do this, right? So we're actually going to create a new node called head, right? And we're just going to do new list node, right? And this node's going to hang back, and we're going to say let prev equal to head, right? This is going to simplify how we return the head of the function, right? Because we can just say return head dot next, right? Then we're going to try and exhaust one of the lists, right? Just like how we tried to exhaust one of the lists when we were merging the arrays, right? And then what we're going to say is L1 is equal to L1. Oh, no, not yet. So we're going to say if L1.val is less than L2.val, right? Then prev, oh, I always mess this one up. Prev.next is going to be equal to L1, right? L1 is going to be equal to L1.next. Else, right, then that means that L2 is smaller. So prev.next is equal to L2, and L2 is equal to L2.next. And then here we have to make sure that we increment L1. No. I think this is okay here. I feel like I'm forgetting something already. This looks okay to me, right? And once we make it out here, one of the lists is exhausted, right? And to do that, right, to put that final element onto the list, right, we can just say, hey, prev.next is going to be equal to if L1 equals null, right? That means we exhausted L1, L2 remains, right? Otherwise, we're just going to say it's equal to L2. Oh, I think we're forgetting something here. Unexpected identifier, L2. What does that even mean, bro? Equals null. Oops, I did the ternary in the wrong order. I knew it. Output is going to be 4. Head.next. I knew. Oh my god. We have to increment prev, man. I knew it. I knew we forgot something, man. I knew it. I always mess this one up, man. Draw the iteration. That's why I put draw the iteration. Don't forget to increment prev, bro. So that actually runs in O of n plus n time, right? With constant space. A home stretch here, boys. Create an array of integers. Find if the array contains any duplicates. The array is not sorted, so this is just going to be a standard. Some of these problems are very similar, man. We're going to say let num of nums. This is the same thing we always do, right? If num in n dict, right? Then we're going to say n dict sub num, right, is equal to n dict sub num plus 1, right? Else we're going to say n dict sub num is the first time we're seeing it. Add 1 to it, right? From here we can just say let key in n dict, right? We're gonna say, hey, if n dict sub key, what am I returning here? Given an array, find if the array contains any duplicates, right? So if n dict sub t, if any value appears more than twice, I think we can actually make this faster by checking up here as well, but it doesn't even matter. right? If it's greater than or equal to 2, right? And it should return false if return true. So okay, we're gonna return true here. And then if we make it out here, that we can return false. Boom, this is gonna run in linear space, constant time. Valid parentheses, this is a cool problem. Given a string S containing just the characters opening parenthesis, closing, opening curly, closing bracket, and so on, right? Determine if the input string is valid. An input string is valid only if open brackets must be closed by the same type of brackets, open brackets must be closed in the correct order. So how do you go about this, right? So you actually need two things. You need a mapping, right? Which is going to allow us to map an opening bracket, right, to a closing bracket. You're going to need a stack, right? So our dictionary here, right, is what's going to allow us, right, to enforce the first rule, which is open brackets must be closed by the same type of brackets, right? And then our stack is going to help us enforce both of the remaining rules, right? And so what we can do is we're going to create the stack here. And so our stack, so we're going to iterate through for let sim of s, right? And what we're going to do is we're going to only add a symbol to the stack if it's an opening symbol, right? So we're going to say if sim in mapping, right? Well, hey, we said we'd only add opening symbols to the stack, so we're going to say stack.push sim, right? We're going to say, okay, if you're not an opening symbol, right, do you, so if we do mapping sub sim, right, mapping sub stack dot length -1 equals sim. So do you close our most recently added opening bracket on the stack? If you do, right, then we're gonna pop it off the stack, right? Because you found your buddy, right? In this function, right, opening closing parenthesis closes opening parenthesis, right? That's great. Otherwise, right, what are you gonna do? We're gonna return false. So if you're not an opening bracket and you don't close the top of the bracket, right, which means you don't close it in the correct order and you're not being closed by the same type of bracket, right, then we're gonna return false. Then at the end, right, our edge case, right, is that we're gonna have to return stack.length equals 0. Why do we have to do that, right? Imagine, right, if we have an input string, right, that's just a whole bunch of opening curly braces, right? What does our algorithm do? We on each iteration we just push it to the stack, right, and then we'd return true, right, if this case wasn't here, right? That's clearly not how that works. So if our stack is not empty, right, then input string is not valid. So this is going to be done in linear space, right, with linear time. And boom. Wait, 130, pause. Hey, we got all our time, boys. I thought we could do this in an hour. I thought I could do this in an hour. Turns out I'm cheeks and delusional. So, hey, it is what it is. So that was 36 random LeetCode problems that I'm practicing intermittently. Probably next week, in a couple weeks, we'll probably do speed run of 100 LeetCode problems. In a year, we're going to speed run 1,700 problems. Pog you. Get ready. But let me know if I mess up any time, space, complexities. Let me know if this was dope. Let me know if this was cheeks. Let me know if I wasted my time. And farewell, my fellow homunculi. I'm about to go to bed.